stoichiometry. Solution stoichiometry is where you take the mole ratio and molarity to determine the mass or moles or whatever you're trying to solve for out of a balanced equation. So let's say we have sodium reacting with water that form sodium hydroxide plus hydrogen gas. Now, a normal problem that you would do is, now this is a solid, by the way. This is a liquid, this is aqueous, and then this is a gas, all right? So balancing this equation out, we have that form, okay? So when we talk about solution stoichiometry, what we typically do is, so if we start, we'll say 25 grams of sodium, all right, and normal question would be, what mass of sodium hydroxide will be produced? Now, another question could be, so we do this in a volume, okay? So let's say we have 100 milliliters of solution. What is the molarity of NaOH after the reaction's concluded, all right? So now this type of problem is a little different. So we're not solving for grams now. What we'd be solving for is the molarity of NaOH. So solution stoichiometry is taking the molarity and dilutions that we talked about last time, and we're applying it to the actual balanced equation. So now this problem, just starting this out, we would take 25 grams of sodium and we would convert this into moles of sodium. All right, so this is going to be where you divide by the molar mass. And then you would take the moles of sodium, convert that into moles of NaOH. Now, this is using the mole ratio, okay? So let's do that right now. Okay, this is the easy part. So the molar mass of sodium, rounding it, is 23 grams per mole. So we're going to divide this by 23 grams per mole. And then we're going to use the mole ratio here, okay? The mole ratio is 2 moles of sodium hydroxide for every 2 moles of sodium. All right, so the grams cancels out, the moles of sodium cancel out, and that will leave you with moles of sodium hydroxide. So doing this, you're going to take 25 divided by 23, which gives me 1.09 moles of sodium hydroxide. Now remember, the 2 over 2 basically cancels out 1 to 1, so it reduces. So now we have moles of sodium hydroxide. Our question is, what is the molarity of sodium hydroxide? All right. Now going back to the last video in the last lecture, we are going to have to make sure we know the moles of sodium hydroxide per liter of solution. And that's my shorthand way of writing solution. So we know the moles of sodium hydroxide. We just calculated that, 1.09 moles of NaOH. Now, right here, I gave you the milliliters of solution. So 100 milliliters is equal to 0.1 liters. So we're going to divide that by 0.100 liters. So when we do that, that gives us an answer of 10.9 molar sodium hydroxide. So when we talk about solution stoichiometry, this is really what we're trying to get ourselves to being able to do, is trying to solve for molarity using the information given. Do y'all understand that part?
Yes.
So another problem might be where if we take HCl, now we're getting into these different types of reactions. So take HCl reacting with sodium hydroxide to form sodium chloride plus water. So this would be an example of a neutralization reaction because you have your acid HCl and you have your sodium hydroxide, which is a base. And so anytime you react an acid with a base, you form salt plus water. And so now in this example, let's say we take, say 15.5 milliliters of a 0.1 molar HCl solution. So we have that volume with that molarity of HCl. All right, what volume of a 0.2 molar NaOH solution would be needed to completely react with HCl. All right, I'll read that again. So you have 15.5 milliliters of 0.1 molar HCl. What volume of a 0.2 molar NaOH solution would be needed to completely react with HCl? Okay, so we've got two pieces of information. We have the given, and then we have our question. All right, so that's our goal, is to solve for the volume. So to do this, just a little bit different, okay? So it's not like our typical roadmap that we were using just a few minutes ago. We're going to have to understand that we're given volume and molarity. From these two, we can calculate the moles of HCl. So how do we do that? Well, first of all, our volume is in milliliters. We need to convert this into liters. So we have 15.5 milliliters. We're going to divide that by 1,000 milliliters per liter. That's going to give me 0.0155 liters of HCl. Now the second thing we're given is the molarity of HCl, which was 0.1 moles of HCl per liter of solution. So what we're going to do is we're going to take the volume and the molarity, and we're going to determine the moles of HCl. So take the volume, and you're going to multiply that by the molarity. Now, if you pay attention to the units, the liters the liters cancel out. So we multiply 0.0155 times 0.1. That gives me 0.00155 moles of HCl. All right. So we're going to take that number there, okay? And I'm going to go back up a little bit here. All right. So write this number down, okay? So that's our number we're going to start with. All right. What our goal now is to go from moles of HCl into moles of NaOH using the mole ratio. So we're going to take the 0.01015 moles of HCl, and we're going to use the mole ratio here. Now the mole ratio for this reaction is simple. It's 1 to 1. So we have 1 mole of NaOH per 1 mole of HCl. So that's going to give you 0.0015 moles of NaOH. Now, our next step, which is the third step, is number 2. This here is number 1. So we have those ordered. So our third step will be taking the moles of NaOH and calculating the molarity of NaOH. So molarity again is moles per liter. So you have your 0.0015 moles of NaOH. Divide that by well, you know what? They give you the molarity, don't they? We need a volume. So scratch that out and write this in. We already know the molarity. That makes it a little bit easier. So all we're gonna do now is solve for volume. If you remember back from math class, we just crisscross these two, right? You bring this up and you bring that down. So volume is equal to 0.0015 moles of NaOH divided by 0.2 molar. All right. So when you do this division, what's going to happen is the moles are going to cancel out, and that's going to leave you with liters. All right. So that gives you 0.0075 liters. Now, in lab, we need to make sure we convert this back into milliliters because we don't use liters with our graduated cylinders. We use milliliters. So what we do here is all we're going to do is multiply by 1,000. All right. So and that gives you 1, 2, 3. That gives you 7.5 milliliters of a 0.2 molar NaOH. So that's the answer here. And we need 7.5 milliliters. So recap here, molarity slash volume gets us moles of HCl. Second step was taking your moles of HCl, converting that into moles of NaOH using the mole ratio. Third step was then taking your volume slash moles of NaOH, not volume, I don't know why I keep saying that, molarity slash moles, and convert that into volume of NaOH needed. So remember that this volume is in liters, and in our fourth step, which was the last step, we took our volume in liters and converted it into volume with milliliters. So this is a full problem, okay? So anytime you see solution stoichiometry and you hear about it, that's what this type of problem is, okay? So this is a direct example of what we refer to as solution stoichiometry. All right. Now, I'm going to scroll back out here for a second. So if you need any notes right there, go ahead and jot them down. If you have any questions, ask me. All right. So we're going to move on then. So as I was talking to you earlier, there's different types of reactions, okay? So the first one that we just looked at is called neutralization. This will help for what we cover next week. So neutralization is where you have an acid reacting with a base to produce salt and water. Second type is precipitation. Precipitation is where you have two solutions reacting to form a solid product. And that solid is what we call precipitation. All right, so good example for this is where we have beaker A, and we're going to get to this next week. So you have beaker A, and then you have beaker B. In beaker A, you have silver ions and nitrate ions, right? So silver nitrate. And then in beaker B, you have sodium ions and chloride ions. So you have sodium chloride. All right, the way this would be set up is you have AgNO3 reacting with NaCl. Now, you mix these two together. Okay, so what you do is you mix them together. So you now have one solution, but what happens in this solution is you form a solid on the bottom. All right, now above you have sodium ions and nitrate ions, but then the solid is AgCl. So you're forming NaNO3 aqueous plus AgCl, which is your solid. So your AgCl is your precipitate because precipitates fall out of a solution. All right. I'm going to write something below here. All right. So we're going to look at solubility rules next time. You guys kind of saw something similar to this in the lab where we talked about soluble versus insoluble. We're going to do more with that next week. All right. So the reason why I say this is because we can apply the same solution stoichiometry with this as we did in the previous problem. All right. So I'm going to write down this reaction we just looked at. So AgNO3 reacting with NaCl. AQ stands for aqueous. It forms NaNO3 plus AgCl solid. Now the nice thing about this is that these are 1 to 1 to 1 to 1 ratio. So this is a balanced equation right off the bat. All right, so let's say we start off with 0.2 molar with a volume of, let's say, 10 milliliters. Okay, so we get, so for the silver nitrate, we've got 0.2 molar and 10 milliliters. What mass of AgCl will be produced from that amount of AgNO3 reacting? So the first thing we're going to do is you're going to take your milliliters, and we're going to go ahead and convert this into liters, which is 0.0100 liters. So just move the decimal place 3 times to the left. Now what we're going to do is we're going to multiply by its molarity. So it's 0.2 moles of AgNO3 for every liter of solution. Now, notice that the liters are going to cancel out. All right. So that's going to give me, so we got 0.01 times 0.2 gives me 0.002 moles of AgNO3. Now we're going to take our 0.002 moles of AgNO3 and we're going to use the mole ratio. So it's 1 mole of AgCl for every 1 mole of AgNO3. So that gives you the same number here. All right. So step 1, step 2, and step 3. Now this is our final step here, right? Because all we got to do now is convert our moles of AgCl into grams of AgCl. Now what we need to do now is calculate the molar mass of AgCl. So I'm going to look at the molar mass of Ag right fast. So Ag is 107, so that's basically, all right, let's do it. 107.87 plus 35.45 gives me, all right, so we're going to multiply this by 143.32 grams per mole. So your moles are going to cancel out here. So 0.002 times that gives me 0.287 grams of AgCl. So that's the mass of AgCl that's going to be produced from this reaction. Any questions on that one? Are y'all following me? Are y'all understanding what we're going through here?
Can you go back for 1 second? I couldn't hear the end.
Is that good?
Mr. Shelton, are you going to post this?
Yeah. Yeah.
Okay.
Portia, you got it?
Oh, yeah, I got it. I'm sorry.
All right. So in your textbook, they give you a problem. It's example 4.8. If you have the old textbook, it's page 157. If you have the new textbook, I don't know what page it's on, but the problem has a separate reaction. So, all right. So in this problem, they give you the balanced equation as 2KCl reacting with lead to nitrate. That's NO3. And that yields PbCl2 solid plus NO3 aqueous. Now, they give you 0.150. Let's see if I can write that better. They give you 0.150 liters of a 0.175 molar PB NO3 solution. All right, so that's the given information. Now, what they're wanting you to solve for is what volume in liters, and they give us to you. And I'm trying to write it the same way, of 0.150 molar KCl solution to completely react. All right, so what we need to do is we're going to take the lead 2 nitrate, the molarity and volume. We're going to react them together. We're going to figure out how many moles of that you have, and then we're going to use that to figure out how much KCl is needed. All right. In this case, what volume of KCl is needed. So step one is like we did before. You're going to take the volume, and we're going to multiply it by the 0.175 molars lead 2 nitrate. All right. So the liters cancel out. That's why you know to do that, because you want your volume to cancel. 0.15 times 0.175, that gives me 0.0263 moles of lead 2 nitrate. All right, now step two, you're going to use the mole ratio. So we're going to take 0.0263 moles of lead 2 nitrate, and we're going to multiply that by 2 moles of KCl for every 1 mole of lead 2 nitrate. Remember, we're using the mole ratio here because you want your lead to go away. All right, now we're going to multiply that by 2, which gives me 0.0525 moles of KCl. Now our step 3 will take the moles of KCl and the molarity and solve for volume. So we're going to have 0.150 molar KCl is equal to 0.0525 moles of KCl divided by the volume. So we're going to solve for volume here. So all I do is that crisscross rule that I was telling you about earlier. And so we're going to have volume is equal to 0.0525 moles divided by 0.150 molar. When you divide this into each other, remember you're going to divide out the moles. So you're going to be left over with 0.350 liters of KCl. Now, in a lab, this would be 30, was that 1, 2, 3? That'd be 350 milliliters of KCl. But the question does not ask for that. The question asks for in liters. So this would be our final answer here.
So you divide it by the given?
Yes. Yep. And just so we can see that clearly, I'm going to highlight it up here. All right, so that's the given there. And that's the given there. Is that what you're asking?
Yes.
Okay, good. And if we take this and this, we have that here. So we can see where the different pieces of information are going.